The experiment found almost nothing. And that was the problem. In 1887, Albert A. Michelson and Edward W. Morley built a machine in Cleveland to detect Earth's motion through a substance almost every physicist thought had to exist. It was called the luminiferous ether, the invisible medium that was supposed to carry light waves through space. If Earth was moving through that ether at roughly 30 kilometers per second, then light should have traveled slightly differently depending on direction. The expected signal was not huge, but it was specific. About 0.4 of a fringe shift in the interference pattern. What they saw was about 0.01 fringe, roughly 1/40th of the classical expectation, effectively null within their uncertainty. A giant floating machine had asked whether Earth was plowing through ether, and the answer came back almost silent. This is no science. The common story says Michelson and Morley instantly proved special relativity. The real story is better. The null result did not finish physics, but it made the old picture harder and harder to keep. To understand why almost nothing mattered, we need to start with an idea that once seemed almost unavoidable. Waves usually wave in something. Sound needs air. Ocean waves need water. So 19th century physicists naturally asked what light was waving in. The ether filled that role beautifully, at least on paper. It gave light a stage, a preferred background, and a way to fit wave optics into the mechanical imagination of the age. That was why the idea had such staying power. It did not sound mystical to physicists of the time. It sounded practical. If light behaved like a wave, and waves needed a carrier, then ether looked less like a guess and more like unfinished engineering. There were already cracks, though. In 1810, François Arago's optical work was described in the supplied historical sources as an early result that did not sit comfortably with simple ether expectations. That did not erase ether. Scientific ideas rarely disappear after one awkward clue. Instead, physicists sharpened the question. If Earth moved through a stationary ether, then there should be an ether wind, like the air felt by a cyclist moving through still weather. Light sent along Earth's motion should make a different trip from light sent sideways. That difference was the target. So the problem became wonderfully concrete. Could you build an instrument sensitive enough to see the ether wind in light itself? The place shift is Cleveland, 1887, in the Case School and Western Reserve Scientific Community, using a basement laboratory arranged for exceptional stability. Michelson and Morley did not try to chase ether directly. They compared two light journeys with an optical interferometer. A beam of light was split into two paths at right angles, reflected by mirrors, and recombined so the waves made bright and dark interference fringes. If one path took slightly longer than the other, the fringes would shift. This was the beauty of the method. It did not need a stopwatch fast enough to time light directly. It turned an almost impossibly small travel time difference into a visible displacement of lines. The clever part was rotation. If the ether wind had a direction through the lab, turning the apparatus should swap which light path fought the wind most strongly. That rotation should have turned the predicted time difference into a measurable fringe shift. But precision has enemies: vibration, heat, alignment, and friction. So the apparatus sat on a massive stone slab floating in mercury, allowing the whole instrument to rotate smoothly while staying mechanically stable. The mercury was not a flourish. It was part of the measurement strategy. A stiff table might jerk, twist, or drag the optics out of alignment. A floating support let the experiment compare angles with far less mechanical disturbance. This is the image to keep in mind. A heavy stone platform floating on liquid metal, built to notice a difference smaller than the eye could casually see. And now the experiment had nowhere to hide. If ether drift was real in the simple classical sense, the fringes should tell the story. Now we move from the room to the eyepiece. This is where the ether wind became a measurement instead of a philosophy. The expected classical signal was about 0.4 of a fringe. That number came from Earth's orbital speed, roughly 30 kilometers per second, and from the way two perpendicular light paths should respond to motion through ether. In the simple model, the arm aligned with the ether wind would not behave exactly like the arm across it. On one leg of the trip, the beam would work against the wind. On the return, it would ride with it. The sideways beam had a different geometry, more like crossing a moving river and returning to the same point. Put those two trips back together, and their waves should no longer line up in quite the same way. So Michelson and Morley rotated the floating apparatus and looked for the pattern to slide. The operational reveal is that the apparatus was not looking for a vague disturbance. It was looking for a repeating pattern tied to angle. If the ether wind crossed the laboratory, then turning the stone slab should make the signal rise, fall, and return in a disciplined cycle. That pattern was the fingerprint. The weight. What moment is that it barely appeared? The reported residual was about 0.01 fringe, tiny compared with the expected effect. That is why people call it a null result. But null does not mean a magic perfect zero written by nature. It means the effect the classical ether wind model predicted was not found at the size it should have appeared. That distinction matters because real experiments live inside uncertainty. The supplied historical data do not let us assign every tiny residual to a specific early systematic error. Temperature gradients, alignment limits, mechanical details, and reading precision all belonged to the practical world of the instrument. This is where the experiment becomes more interesting, not less. A messy laboratory could explain small deviations. It could not comfortably hide a signal expected to be about 40 times larger than the reported residual. The apparatus did not need perfection to challenge the simple ether wind. It only needed enough sensitivity to show that the predicted shift was missing at the expected scale. But none of that rescued the simple prediction. The classical ether wind should have been large enough for the apparatus to see. Instead, the machine returned a near silence. And that silence created the next, harder question. Was the ether being dragged along with Earth? Was the apparatus somehow contracting? Or was the whole preferred frame picture wrong? The story now leaves the Cleveland laboratory and enters the theoretical workshop. A null result is not automatically a new theory. It is a constraint. After 1887, physicists could still try to keep ether, but the simple version had become expensive. In 1889, George FitzGerald proposed that objects might contract along the direction of motion through ether. In the 1890s and early 1900s, Hendrik Lorentz developed local time, contraction, and transformation ideas that could account for the missing drift. These ideas could explain why the expected fringe shift failed to appear. But notice the price. To save the old stage, theory had to allow the measuring rods on that stage to change with motion. That is a deep clue, because the instrument was not merely measuring light, it was also testing assumptions about length, motion, and what counts as rest. The instrument had not merely produced a disappointing data point, it forced theory to become stranger, more mathematical, and less tied to everyday mechanical intuition. This is where the popular myth gets tempting. It feels satisfying to say one experiment killed ether and created relativity. But the evidence-led version is more careful. The Michelson-Morley experiment tested ether drift expectations, not every claim of special relativity. Historical interferometer experiments also do not directly determine the one-way speed of light unless you adopt a clock synchronization convention. That caveat does not weaken the story. It sharpens it. Michelson and Morley were comparing round trips along perpendicular arms, and that was enough to make the simple ether drift picture struggle. So the result was powerful, but not alone. That makes it less like a final verdict and more like a door that could no longer be closed. Now the place shift is a desk in 1905. Albert Einstein's special relativity did not begin by patching a failed ether machine. It began from two principles. The laws of physics are the same in inertial frames, and the speed of light in vacuum is constant for all inertial observers. That is the mental model shift. Instead of asking how fast the laboratory moved through a hidden rest frame, relativity asked what measurements different observers could consistently agree on. Suddenly, the stubborn fringes made a different kind of sense. The near-null result fit a world where there was no detectable ether wind defining an absolute state of rest. But even here, precision matters. The supplied data do not identify one single experiment that establishes the full special relativity framework by itself. Later tests, including Kennedy Thorndike and Ives Stilwell, addressed additional predictions and helped tighten the case. So what did Michelson and Morley really do? They made the ether worldview measurable, and then measured a result far too small for the simple version to survive comfortably. That is the late aha. The experiment's power was not that it shouted a new theory, it whispered that the old one had run out of room. And so we return to the floating stone slab in Mercury. It looks like a machine built to find something. Instead, its most famous contribution came from what it failed to find at the expected scale. That failure was not empty. It narrowed the world. It made easy explanations harder, forced better questions, and helped move physics toward a view where space and time were not the fixed stage people had imagined. The machine in Cleveland did not hand scientists a finished universe. It handed them a missing signal, measured carefully enough that every serious explanation had to answer for it. This null result reminds us that evidence does not always arrive as a dramatic signal. Sometimes the missing shift is the message. But Michelson-Morley was not the only experiment where almost nothing forced physics to rethink what counted as real. I'm here to help you know how old questions become modern experiments. Which Michelson-Morley signal would you trust first? The expected ether drift or the near-null fringe shift? Tell me in the comments. Thanks for watching.